So we're going to be calculating average atomic mass in this video and finding sort of what that means in terms of the actual mass of an atom and the different isotopes of each element that exist out there in nature and how we study them. In reality, if you recall from earlier in your notes, this slide, there are isotopes of nearly every element, various isotopes of nearly every element out there that's naturally occurring in the universe. And so, for example, in this slide I told you about three isotopes of carbon, carbon-12, carbon-13, and carbon-14, and that their differences come in the number of neutrons and therefore in their mass, atomic mass as well. So carbons 12, 13, and 14 are each different by 1 AMU, and out there in the universe there are various amounts of carbons 12, 13, and 14, all mixed together. So if you picked up a bottle that was pure carbon, or if you looked at carbon in a pure form, like in a nice pure diamond or a piece of graphite for your pencil, the carbons in that sample would be of all the different types, carbon 12, 13, and 14. If we're using carbon in a chemical reaction, we need to be able to know what the mass of the average atom in that sample is, because when elements react with each other, they react atom to atom. They don't react gram to gram. They react atom to atom. So one atom of this and 4 atoms of this can make 1 molecule of something, for example. And so we need to be able to keep track of the average mass of a carbon atom in a sample of carbon or in any other element's sample as well. So to do that, we calculate what we call average atomic mass. And average atomic mass is needed because, as I mentioned, in nature, all of the isotopes of an element are found mixed all together. You can't go to a catalog and order a bottle of pure carbon-12 very easily. In fact, you can't get it at all. It's impossible. They all exist out there all together. And so we can't get good just carbon-12s and keep our reactions simple. It's going to be a blend of all of them. When using an element in a reaction, we use average mass of all the isotopes. And you can see here that we've got platinum, again, as I mentioned in an earlier slide, the platinum on our periodic table. We talked about the atomic number earlier. Here, the arrow you see is pointing at the little red number on your periodic table. And that number is for platinum's average atomic mass. If you look at your periodic table in the key, it's not called average atomic mass. They call it something else. We're going to change that to average atomic mass, not atomic weight, but average atomic mass. And out there then in the universe, we're saying then that platinum, on the average, an atom of platinum has a mass of 195.08 AMUs. What we should note is that if that's the average mass, that there is no such platinum atom out there in the universe. There is no platinum that has a mass of 195.08. The average represents sort of the balance of all of those different isotopes of platinum. There are actually 5 stable isotopes of platinum that we know of in the universe, and when they blend all together, the average mass is around 195.08. So this is not too different from if I say, let's give you a 10-point quiz, and at the end I say your class average was 8.3. Well, no one scored an 8.3. But it gives us a pretty good idea of the overall class's performance when I say the average was 8.3. You'd probably guess that some had a 10, and a 9, and an 8, and a 7, maybe a 6. But on the average, somewhere in the neighborhood of an 8 or a little better was the score that most of you got. And so the average tells us a lot about the big picture, but doesn't necessarily give us the details, and sometimes that's okay. This is the equation for average atomic mass. To find average atomic mass, what we do is we take the mass of the first isotope of the element times its percent abundance written as a decimal, plus the mass of the second isotope times its percent abundance written as a decimal, and so on and so on. There might be a third, fourth, fifth isotope, and if that were the case, you would have 5 masses times 5% abundances written as decimals. Now, what is this percent abundance written as a decimal business? I just want to show you what we mean by that. Percent abundance written as a decimal would mean that if your percent abundance, let's say that 60% of the atoms were a certain mass, 60% abundance would mean that 6 out of 10 or 60 out of 100, right? To write that as a decimal, we would write it as 0.600 if we kept our significant figures written as a decimal. Or if 25% would be written as 0.25. It's important to remember that on really small percentages that you still need to move your decimal over twice. And if you notice, that's essentially what we're doing, right? We're taking the decimal point and moving it over twice to get percentage written as a decimal. Same thing here. We're bringing the decimal over 2 positions, more or less dividing by 100. So you take percent and then divide it by 100 to get it written as a decimal, into decimal form. And so if we had a very small percentage, like let's say 0.73%, to write that as a decimal, you would still need to move the decimal over twice. So as a decimal, you'd bring that over 2 positions, and you would get 0. Notice we filled it in here with another 0.0073. So a small number, a small percentage, like 0.73%, becomes a very, very small looking number when written as a decimal. And that will sometimes be the case. So don't forget to move those over. In the long and the short of it, essentially, all the percentages should add up to 100%, and therefore all the percent abundances written as a decimal should add up to 1. So if it was 75% and 25%, that adds up to 100. Written as a decimal, that would be 0.75 and 0.25, and that would add up to 1. So whether you write it as a percentage or a decimal, you should have the whole total when you do that.